Good morning. My name is Grennon Gurney. Today I'll be talking about leveraging homogeneity for machine learning prediction of spatiotemporal chaos with limited training data. So going into this project, we're motivated by the fact that a lot of real world systems have spatiotemporal chaos. For instance, weather patterns is a very prevalent example, but in many cases, there's insufficient training data for creating machine learning methods that can predict the future evolution of these systems. In order to rectify this, we consider the case where dynamical systems are homogeneous in space and leverage this homogeneity to facilitate useful training predictions with limited data. And we're using the Kuramoto-Sivashinsky equation, which is seen evolving in time here. This equation is a nonlinear spatially homogeneous partial differential equation used in plasma physics, fluid dynamics, and flame propagation. Something important to know is that this homogeneity happens because no term explicitly depends on position. So the overall global dynamics are the same throughout the spatial region. However, due to the initial conditions, there are some differences, as you can see here. So in order to do machine learning prediction on this, we break the region up into smaller subregions and analyze these with their own distinct neural networks. So, and note the colors here. Doing this training on each neural network in each region in space allows us to capture that local dynamics as well as the global changing of the dynamics. And that's encapsulated in these output weight layers that kind of take in those dynamics and predict what's going to be happening next. We also have a notion of locality due to overlaps at the border of these regions so that we can see what's happening as we're going from region to region. The next part is that because the system is homogeneous, as we increase the time over which we are doing training, we find that these output layers tend to look similar as time goes on. That motivates our new approach, which is leveraging the homogeneity of the system with a single output layer trained on the union of all training data. So we can see here this purple, blue, blue, red, these squiggly lines, they're fed in, their dynamics are studied by the system. Then afterwards, the next region is studied by the system and more after that for as many as we have. By getting this, we're capturing the dynamics over the entirety of the spatial regions, but with one reservoir. So if we have T amount of training data going back in time and reservoirs, instead of training each neural network system, each reservoir on its T amount of data for its specific region, we can train on effectively N times T, where N is the number of regions over which we're training. So we can manipulate that data to get better predictions. We find that using this method that leverages homogeneity gives much better predictions compared to the existing method. These plots are the difference of the true evolution of the Kuramoto-Sivashinsky equation compared to our predictions. And we can see here this region where there is very little error compared to this older method that we have. These dotted lines represent the valid prediction time, which is the time after which our predictions diverge from the solution. That solution is no longer beneficial to be studied with these methods. Next, we look at varying the training length and seeing its effect on the valid prediction time. And we can see here an important result that we have a notable improvement for these shorter training lengths compared to the existing methods. So far we've shown that the machine learning approach to forecasting spatiotemporally chaotic systems can benefit from a chaining scheme that incorporates this homogeneity and can facilitate useful predictions within this training data. The next step is adding in homogeneity to this system. Because this is a very illustrative example, we can modify the KS system to include terms that do depend weakly and then more strongly on its spatial regions and study the extent to which our model can accurately predict the dynamics of the system. I'd like to thank everyone in Trend, Daniel Serrano, my mentor Declan, and then professors Michelle Gervin, Thomas Anderson, and Edward Ott. And Rob. Thank you very much.